Up to this point, we've been looking at the use of templates where we're parameterizing by type alone. So, for example, a stack of int, a stack of simple string, a stack of throw exception, and so on. Now we're going to look at a case where we can have templates that not just parameterize based on type, but actually parameterize based on values. And that'll allow us to implement yet another variant of our stack class where we're going to give the size of the stack as a template parameter. And this will be kind of fun. So let's go take a look at how this works. This is going to require a few other changes, which we'll talk about as we go through this. So take a look at this stack. This stack is a stack of type name t, just like we had before. But now we have a second template parameter, which is the size as a size t. So this is a value, not a type. And if you take a look down here, you'll see that we actually had to get rid of some of the methods. We don't need all the methods we had before. We keep the bulk of them, but a few things have changed a bit. And if you take a look at the implementation, for example, one thing we don't need is swap. We no longer need a swap, and you'll see why in a second. The implementation here defines us an array of size value types, where value type, of course, is this trait that's defined to be type t. So now we have a statically allocated array whose size can be changed, but there's no dynamic allocation involved. So that's going to clean quite a few things up because we don't have to worry about exceptions corrupting the state and leaking memory. It can still corrupt the state, but it won't leak memory. In fact, the semantics of this class are subtly different from what we've seen before. So here's the main program. We're going to make ourselves a stack of 3 elements, and then we're going to go ahead and do various operations. We can copy things. As long as you're copying from a stack of the right size, the same size, it'll work fine. We do is full, push, is empty, pop, top. Everything's pretty much the same as before. And then we can go ahead and do the copy assignment operation. You'll see, however, there are a few little differences here because of the way in which we've changed this to work with a fixed size stack. In particular, we no longer have this technique of doing move semantics because we can't lobotomize the right-hand side because it's a fixed size array that's statically defined. So we get rid of the move assignment operator and we get rid of the move constructor. We don't need those anymore. But we do have the other operations like push and the r-value push and also the in place. So let's go take a look at the implementation. It's quite a bit simpler because we don't have to worry about dynamic memory allocation. So in this particular case, this is our constructor, our copy constructor, and you can see we don't have to worry about allocating anything dynamically. So if an exception is thrown, oh well, we didn't allocate the memory dynamically, so we don't have to worry about cleaning it up. And the assignment operator is also a little different too. Because of the fact that we're not using pointers, we can't use our swap trick the same way we did before. So this code here, of course, will not leak memory, but it won't have strong exception guarantees. Because if something throws an exception midway through, then we have corrupted the left-hand side a bit. We won't leak memory because there's no memory allocated dynamically at all, but we can end up corrupting the left-hand side. So the key rule here to remember is if you use these statically defined types, statically defined template parameters, then you get simpler exception cleanup semantics, but you don't get the strong exception guarantees because there's just no way to do that. The strong exception guarantees work because you can create a temporary object, and then if it finishes correctly, you can swap it by doing a pointer swap, which will not throw an exception. So if that's the price you pay for getting rid of dynamic memory allocation. So it's kind of a pro and a con in this case. So this implementation is kind of fun. Let's go ahead and run it. It doesn't really do anything particularly interesting other than just show that you can use templates that will be parameterized by type and value. So that's the next topic I wanted to cover with you.